So section 6.1, it's number 6C, is the one we have problems with. So let's just go through 6 altogether, just in case anyone had problems with this. So it says consider this equation. Okay, so this side is equal to this side. It's an equation. What are the non-permissible values in radians for this equation? Okay, so things we have to keep in mind: we cannot divide by zero. Or infinity, right? Or yes, and we cannot have an undefined value in any part of the equation, numerator or a denominator. So those are the ones we're looking for. So I'm looking at a denominator down here. 1 plus cos x cannot equal 0. So that means cos x cannot equal negative 1. So what are the x values associated with negative 1 for cos? So negative 1, 0 is on the unit circle, and that's going to be cos. So that's going to be pi. Okay, so we cannot have pi. Anything else there? Can we have a 0 up here? Can this equal 0? The numerator? Yeah, numerators can equal 0. No problem. Denominators, now tan is another one, right? Tan, we have undefined values all over the place. So let's figure out, now, it doesn't give us, in A, it doesn't actually give us a specified domain. Put that away, please. Put them all away. I don't want to see them. Okay? It doesn't give us a specified domain. So that means you probably need to do general solutions. Okay? General solutions. Now, B does give us a specified domain. So that's different. But if it just says A, we're going to have to do general solutions. So we'll keep this in mind. Again, pi, so this is plus n 2 pi n, right, or n 2 pi radians. It's just every multiple of that. Okay, so we'll keep that in mind. There may be others here. So tan of x, all right, where is tan of x undefined or 0? Well, would it be 0 in certain places? Remember, tan is what? Sine over cos. So here, sine over cos. So at 0, x cannot equal 0. Does that make sense? Because it would be 0 over 1. Anywhere else? Well, pi, 0 over negative 1. So we already have that. And what about this one? What is this? This is 0, 1. And this is 0, negative 1. So is pi defined here at pi over 2 and 3 pi over 2? Is it too early in the morning here, or am I going too fast? So tell me about tan at pi over 2. This is the point 0, 1. Mm-hmm. It is what? So tangent of x at pi over 2 is what? Oh, okay, you could think of the graph as well. So tan looks like this, right? Where are these asymptotes here? Pi over 2. So it's not 0, it's actually undefined. So 1, it would be 1 divided by 0. So it would be the sine value of 1 divided by the cos value of 0. So we can't do pi over 2 either. Okay? And we can't do 3 pi over 2 either, because that is also undefined. That would be negative 1 divided by 0. Yeah. So this would be 1 pi over 2. This is 2 pi over 2. And this is 3 pi over 2. And this would be 4 pi over 2.
Why did didn't get pi over 2, pi, 3 pi over 2?
Yeah. So we're not quite. Yeah. So we're not done yet. What you want to do is you want to take a look at. Oh, this is not equal to. You want to take a look at all this, and is there a way we can better summarize this? You could take each one and add n 2 pi or 2 pi n, whatever. But yeah, there's a simpler way we could do that. We understand that it's every multiple of pi over 2, right? So it's 0 plus any multiple of pi over 2. And where n is an element of what? Yeah, integers, right? So x cannot equal this right here. I think that would be your answer for A. Yes, not equal. Thank you. Not equal. X cannot equal. Keep forgetting that slash there. Okay, so you want to confirm that with your solution manual there if you want. But that's how you. That's right. That's how you get to that. So 0, pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2, whatever. Good? For A? All right, A is done. B, graph the two sides of the equation using technology over this domain. Could it be an identity? Now, how do we know if it could be an identity? What would have to happen for this to be an identity? Any ideas? There shouldn't be any.
Counterexample.
Okay, so there should be no counterexample. There should be no value of x that makes this equation not true. Okay, so what does that mean for the graphs? What would the graphs look like? The same. The graph should look exactly identical. Yeah. Because that means that for every x value, both graphs have the same y value. Every x value, the same y value. So the graph should look exactly the same. So if you don't have a graphing calculator with you right now, why don't you grab one, and let's do this. Let's graph both sides of the equation. Okay, so you guys have done this on your graphing calculators. I did this on Desmos here, so let's just take a look. So if you graph both of these individuals, so again, what you really want to do is you want to graph y equals the left side and y equals the right side, just like I've done here.
Oh, it's frozen.
Frozen? Sorry. Is that good? Okay, so what I'm going to do is I'm going to light up this first one here, and it should look something like this. So I don't know if you guys, did you guys have something like this on your calculator looking like that? Okay, so it probably is an identity. I mean, we can't see everything. So again, a proof that something is an identity involves more than just checking a bunch of values. But this would be checking a whole bunch of values over the specified domain to see if it could be an identity. So notice here it says, could it be an identity? This is not proving it, but this is like a really good case. So when I light this one up, if it's exactly the same, then it could be an identity. So here we go. Look at that. It could be an identity. So this blue graph and the red graph right here, see, are the same. Put them on, off. They're exactly the same. So this definitely could be an identity. And I think it asked from what, 0 to 2 pi? Or yeah, from 0 to 2 pi. So 2 pi would be about 6.28, so somewhere around here. Right there. 2 pi. And yeah, so we do have some values that are, they're going to be an issue, non-permissible, but it looks like the graphs are the same there. So, okay, so that's how you would check graphically. All right, so we want to focus on C. That was the initial question here. We had trouble with C. So we want to verify that the equation is true when x equals pi over 4. Okay, so again, verifying that it's true is simply putting pi over 4 in for x and seeing if the left side agrees with the right side. That's all it is. So we're going to do that. We're just going to put in pi over 4 into each side. Yeah, I mean, sorry? Yeah, so use exact values for each expression of the equation. So what you would do is you could continue on like I did here. I just checked at this stage the decimal, so it looks like we're on the way. When it says exact values, you will have to simplify the terms, flip and multiply, get everything to be exactly the same. Okay? That's the part of the... Okay. All right. Well, okay, fine. Let's just quickly do that then. Okay, so this is the point we're at here. So this right here we said was 1/2. This is 1 plus root 2 over 2. Now, can we simplify that? So that's 2 plus root 2 over 2. This one here would be just 1 minus root 2 over 2. So if you keep going with that here, when you divide by a fraction, this is technically a fraction, you flip and multiply, right? So it would be like this, 2 plus root 2. And this would be, again, 2 minus root 2 all over 2. So these twos cancel out like that. So you have 1 over 2 plus root 2. And here you have 2 minus root 2 over 2. So again, can you get these to be looking the same? Well, if we go back to this is 1 minus root 2 over 2. Okay? And so how do we get this? Now this can be a little bit tricky. What you might want to do here is to rationalize this denominator is one thing you could do, because you can't separate these like you can separate the top ones. So this would be a little trick here. 2 minus root 2. If you do that, that's multiplying by something called the conjugate, which we're going to talk more about as we move through these sections. But that's a way to, because see, look at this is a rational denominator over here. This is an irrational. So when you do this, you get a difference of squares on the bottom. So that is like, what's that? 4 minus 4 root 2 plus, so minus 2 root 2 plus 2 root 2, and then minus 2. And over here you just have 2 minus root 2. So this over here on the left side becomes 2 minus root 2 over 2. And this one we had earlier was that. So in this part, this is the tricky part, and if you want to rationalize a denominator, then you'd have to multiply it by the conjugate, which, if it's a binomial, the conjugate is the same first and last terms, just with a different sign, because then you get a difference of squares, and that root sign goes away. Because when you square a square root, then it goes away. Okay? So that's the verification there using the exact values.